Sorry, are there any questions?
Yeah, this is a question from Swapnil. I only understood about 5% of your talk, but relating it back to the previous talk today, is there any notion of goals being achieved by the imposition of a bottleneck in your approach?
Sorry, come again?
Is there any notion of goals being achieved by imposition of a bottleneck?
Not really. I've tried to relate it to the more conventional form of the economic utility theory rather than going for abstract things like bottlenecks.
So how would you expect goals to be achieved then?
Well, it's pretty much the same as in the case of the reinforcement learning frame. Maximize the utility over future system. That's how it is.
Next question. Okay, so I have a question. I find it very impressive how your three talks are really related in the sense that we are building from the theory to Occam, Occam to the world to utility functions. So that's really the same thing from three different point of views. I was wondering if you saw how this could converge in one unique thing, maybe, or where?
Yeah, I think it can, for sure. As a matter of fact, personally, I'm of the opinion that there are no such disparities, and all the principles underlying the underlying intelligent behavior should come from some unique theory.
I think somewhat is required to Alex's framework more concretely as well, but in spirit, some connection also to your work. But he talked about specialization, which is in a sense, when I go from one machine to another, if I pick a very specific return function, in much more specific like mass induction, it would in a sense be like specialization, even though I try to keep universality to keep that, well, I think Alex was prepared to give it up, I think, for the specific task, if that's correct.
Okay, my talk was only about universal induction, but of course one can consider specialization in universal intelligence settings, and here we can converge in this sense. It's the first thing, and of course if we are talking about embedded artificial intelligence, which is a part of the world, then it should perform operations in some efficient way. And my belief is that universe is itself universal intelligence. It's simply not specialized universal intelligence, and quantum mechanics and physical laws of emergence are also something similar to universal search and model construction, but not specialized. So I think that it is possible to converge all these things together.
So, do you three think that we should use our knowledge of the current laws of physics as the best reference machine we have now? Or should we use some transformation of that or something completely different?
Do you have a choice?
Yeah. Oh, I didn't. What, can you present your thought maybe?
Could you tell me of some theory more profound than the physical laws?
So you're saying actually that any reference language that we may use is eventually based on the laws of physics through computers and all that?
Well, I think they are kind of different ways of looking at the same aspect. It's like Newton could have discovered gravity falling down from the building rather than an apple falling on his head. So it's kind of two different ways of looking at the same aspect, from the viewpoint of computation or going from the viewpoint of physics. As I mentioned earlier in the talk, there are no disparities in science. We should treat science as a unique embodiment of physics.
I take quite a different perspective. I don't think you need to know quantum mechanics to do general artificial intelligence at all, and I also don't even think that physics is the most profound. I think that is something we want to drop behind us and see much of that stuff as more subjective than the forced objectivity that they try to push on things. They try to put forced objectivity, the probabilities. They have to demand that this cat is both alive and dead, and all kind of funky stuff to try to keep this view that they're dealing with something objective. I think they're subjective and they are an observer of the universe, and they have uncertainty about all kind of stuff. I think truly moving over to the more of an alien setting, I think might gain enough for physics the other way. I think we should try to claim the most fundamental ground for them.
You're talking about the Schrodinger's cat paradox. It's been almost 20 years since it's been solved using the quantum recurrence theory. So it's no longer a paradox. We might want to move on.
Well, it indeed depends on how do you understand your question, because as you have said, that every reference machine is implicitly depends on physics, but I agree that we don't need to know quantum mechanics to work in artificial intelligence.
Okay, mainly because humans were there and wanted to use much quantum mechanics to do usual stuff?
Yes.
Okay.
I have a question about the specialization of programs. So I have to look at the paper because I didn't understand everything, but you said that these specializations are not Turing complete, is that right?
Sorry, specialization of what?
The program specializations, or these projections, they are no longer searching in Turing complete space, is that correct? Or was I misunderstanding?
Could you please repeat?
He asked if the specializations are Turing complete or not.
So you're asking if the problem of specialization is Turing complete?
I mean, the search space after specialization is less than Turing complete, correct? Or did I misunderstand?
Okay.
Can you create any program?
Well, I'm not sure that I correctly understand your question, but there are two aspects. First of all, specialization is in general undecidable. So you cannot specialize efficiently any program with respect to any parameter. This is the first point. But we can consider some specific cases in which we can gain some exponential speed up. And if we consider mass induction settings, that yes, after specialization we get a method which works in non-Turing complete space. So this is why we can get much faster methods than exclusive search.
And can you precise exactly, or is it possible to precise what is the search space, the set of programs that you can generate? Is it, for example, multi-recursive or complex programs or anything like that? Or is it something that is not clear for you yet?
I think that it's not clear right now.
Any questions?
My comments and question is for Peter. As a software engineer, I'm very pleased that you rigorously proven that Python is a superior language to Java, and I look forward to sharing notes with my colleagues. But my serious question is, clearly Occam's razor does not always hold in all real-world contexts. Sometimes the simplest explanation is in fact not sufficiently correct. So I was wondering if you could explain whether you think it's possible and how it might be possible for a system biased by Occam's razor to produce a program that can correctly predict when it should abandon Occam's razor to some extent in order to achieve a sufficiently correct program.
Well, so there's two answers. If you do usual like Solomon production or IC, the thing that if you have a very complex solution, being the best one to take a lot longer to find it, though eventually it's going to find it, but in Solomon production, the bound changes with complexity of a true hypothesis. So it takes us a lot longer. Well, what I want to do here is in that case, change the reference framework somehow, fix it so that if one then finds a way of seeing it so that it becomes a simple solution. But if it's something that occurs often, at least, I think that's something we often do. That something is complex for a while, and then somehow we change our way of thinking about it, our concepts, and suddenly the new concepts, or the new tools that we build, suddenly becomes simple while it was more complex thing to begin with.
Can I follow up? So it sounds to me like what you just said, please correct me if I misunderstand, that what you're doing is rather than looking for a more complex solution that is better, that you are changing the definition of better, right? Because we can talk about a program
of complex, not better, keep better. You have to keep what's better, but I'm trying to change what's complex.
You're trying to change the definition of complex.
It's completely dependent on reference machines. So try to build in common complexity somewhere in the machine so that it's easy then to work with it. Like when you create a Python package or something horrible. And then like you make a Tiana package that Joshua's team built, so there are all these complexities, deep learning, but suddenly you can write in a few lines of Python. So it might be quite complex thing, but suddenly becomes short and simple as long as you don't dig into the whole thing underneath, but it's sort of packed into the reference framework.
Thank you.
This session seemed to be an impressive representation for the theory side of AGI. And I can see that there are attempts to move from pure theory to pragmatic side as well. What I'm seeing here are all attempts essentially to go directly from the theory to gradually make it to somewhere where there's something that's actually pragmatic. Another way theory can inform is to directly put constraints on or provide guidance to directly more pragmatic efforts. I'm wondering whether in any of the work that you guys have been involved with, as we've seen here, whether there is information from theory that should help those of us who are sort of come from the more pragmatic side.
I've done work on axiomatizing rationality of various forms, where that leaves a big class of agents that after one has axiomatized rationality, which one then can work fully pragmatically within. One have some guidance on what kind of options to consider, but there's still quite a lot of options left. One can be very pragmatic within that. So I believe that would be quite a good approach, both for being pragmatic, both for how to develop theory that some sort of bounds are mostly relevant within those classes of rational agents, while some sort of worst case bounds can be achieved by very bad agents doing very bad things, just that it doesn't hurt the worst case bounds. But also can be good for evaluating, when we evaluate agents empirically, if one look for a lot of different experiments and finds cherry pick experiments or overfit experiments. But if you have restrained classes of agents to consider, you also dealing with that problem to some extent. So we quite unusual in my community to deal with is try to axiommatize what agents to consider not. People don't really try to restrict themselves at all, but I think it's quite useful to try to figure out what is a rational agent. And I got a bit beyond just to maximize expect utility maximizer be able to allow, for example, some sort of optimistic behavior in some situations. So it is quite large class and but still it rules out plenty of things around, which I think should be ruled out.
Well, thank you. Let's thank the speaker again. If you have other questions.